All right. Welcome to the 5th annual Family Lecture. This lecture series is made possible by a generous gift from the Arnold family, and I'm pleased to acknowledge Doug Arnold and Carmen Calderer in the audience who represent the family. So before we start, I want to say a few words about the Institute for Mathematics and its applications. The IMA is the National Science Foundation Mathematical Science Research Institute. It was established 32 years ago with the mission of bringing together the brightest minds in mathematics and the sciences to solve major problems and challenges from science, technology, and society. I'm very pleased to introduce tonight's speaker, Professor Helmut Pottmann. Dr. Pottmann received his PhD degree from the Vienna University of Technology in 1983. He became professor at the same institution in 1992. He's the head of the geometric modeling and industrial geometry group. He has held visiting positions at the University of California in Davis and also at Tsinghua University in Beijing. He currently holds dual positions at Vienna and also at the King Abdullah University of Science and Technology, where he is the founding director of the Geometric Modeling and Scientific Visualization Center. He also serves as scientific advisor to Evolute, a company based in Vienna that specializes in geometric modeling in architecture and industrial design. He's the author of two very successful books, Computational Line Geometry and Architectural Geometry. Both of them are available on Amazon. He is a prolific writer and has published more than almost 200 research articles. He's well known for his work in geometric modeling, differential geometry, approximation theory, and numerical analysis. He was recipient of the John Gregory Memorial Award in 2008. The award is given every 3 years to an individual who has made fundamental contribution to the field of geometric modeling. Tonight's lecture is entitled Mathematics in Modern Architecture. Please join me in a warm welcome to Professor Helmut.
Yeah, thank you very much, Fadil, for this much too nice introduction. And thank you for inviting me. Thanks to the Arnold family for supporting this event. And thanks to you for coming to this talk despite this terrible weather outside. So I'm pretty impressed. Yeah, the IMA is focusing on bringing together scientists, engineers, and mathematicians. But today I'm talking about architecture. And an architect would not consider himself really an engineer. It is a little bit related to art and to philosophy. And so I thought I will start by defining the involved professions. As you know, the mathematicians like to start out with some definitions. So let me start. An architect is said to be a man who knows a very little about a great deal and keeps knowing less and less about more and more until he knows practically nothing about everything. Whereas, on the other hand, an engineer is a man who knows a great deal about very little and who goes along knowing more and more about less and less until finally he knows practically everything about nothing. Then the contractors start out knowing practically everything about everything but end up by knowing nothing about anything due to association with architects and engineers. And finally, you may know this, according to Charles Darwin, a mathematician is a blind man in a dark room looking for a black cat which isn't there. So after we are prepared with the basic definitions of the involved professions, we can move along. And I'm not going to talk about this ancient relation between mathematics and architecture, but I'm talking about contemporary architecture. And we are looking at designs like this. This is a design by Zaha Hadid architect. Or like this. This is a design also by Zaha Hadid, recently opened in Seoul in South Korea. And if you look at this structure, that is of high geometric complexity, not just on the outside, as you see here, but also in the interior. Another example for this type of architecture I'm talking about today is the Yas Island Marina Hotel in Abu Dhabi. Maybe those of you who like to watch the Formula One races, there is one race usually in November in Abu Dhabi, and along this racetrack you find this structure, and you see it also on TV when they broadcast this race. Yeah, I'm talking about what is called freeform architecture, because these shapes which are used there, they are not just employing the standard forms of geometry which you learn in high school, like a sphere, a cylinder, a cone, and so on. This is much more complicated. And you can imagine that the realization, the actual manufacturing, the fabrication, the construction of such structures is challenging, and it is quite costly. And one reason for the trouble is that the available digital design technology is not really adapted to the demands in this area. And let me dive a little bit into this digital design. This started out in the 1960s, largely motivated by applications in the automotive industry, and it led to the development of what we call now CAD-CAM technology that aims at a completely digital workflow from the design to the production. And one part that is mathematically very interesting is the digital design of these general shapes, free-form curves and surfaces, which actually involves a lot of mathematics, but today I'm not going to talk about this part of mathematics. So this is a transition from the hand drawing, where you also had tools like this one shown here on this slide, which allowed you to draw some curves that are not in these elementary shapes, was a transition to digital design, where the designer now can place some control points, as we say, and by manipulating these points, automatically this shape, in this case this curve, will change and adapt a desired shape. There is a well-known relation between the so-called control polygon and the shape, and designers who are experienced in using this, they know how the shape will react. And this does not only hold for curves, it is also true for surfaces. You can manipulate these shapes just by manipulating these control points on the screen. But afterwards, it comes to production. And the production of a lot of shapes is based on numerically controlled milling machines. So they are controlled by the computer. These milling machines produce these so-called molds, and the molds are then used to produce the actual pieces. But mold fabrication is a costly thing. That's not easy, and it is also expensive. But with a single mold, you can produce many pieces, and then it pays off to do it. Nowadays, we also have 3D printing that becomes mature, but is usually employed only for customized products of typically relatively small size. So, of course, the architects moved from the traditional drawing, hand drawing, and then drafting with ruler and so on, to digital tools. But these tools have been developed for different industries. So this shows a design by Zaha Hadid architects, and an expert in computer-aided design will immediately see how this has been constructed. But if you actually have to fabricate it on this large scale, this is an office building with many floors, as you see, this glass facade, this is not simple at all. You cannot build a structure like this. This is, by the way, also a design by Zaha Hadid architects. You cannot build it in a monolithic way, just this single piece. You cannot produce a mold for this huge piece. There's no way, right? So you have to break it up into panels, into smaller pieces, which you assemble together. However, if this is really free form, then all these panels will be slightly different. There will be no two identical panels, which is bad news, because the production of each of these panels would require at least a unique machine configuration, or even worse, manufacturing a unique mold. And the mold manufacturing is more expensive than later the fabrication of the panel itself. So this is actually too costly and largely infeasible. So the question is, are there alternatives? Can we build such structures despite these obstacles? Well, there's more to be considered, because this skin, these glass panels, they do not fly somewhere in there. They have to be mounted on some substructure which has to hold the panels. So there's a subconstruction which has to be aligned with parts of the interior, like in this case with certain floors. Then you have to consider the statics. Of course, this object has to be stand. We are talking here about architecture. The logistics is a problem, because if you look at such a freeform structure, in this case made up by flat triangular panels, typically no two triangles will be exactly the same. So you have to be careful to mount the right panels. And the solutions of most of these problems actually require some mathematics. And I would like to illustrate a little bit which type of mathematics is involved there. So let us think a little bit, what can we do? Of course, these totally general curved panels will be difficult to realize, and one will have to look at simpler alternatives, and the simplest for sure is a flat panel. So is this trivial? A flat panel? It turns out is not, because a preferred panel shape would be quadrilateral panels. So this is thought to be a skin piece put together by flat quadrilateral panels. And as we will see a little later, this has a lot of mathematics involved. It is not easy to panelize a given shape in such a way. So here is then a rendering. Then you will say, why do you take quadrilaterals? Take triangles. Triangles are flat, yeah? But these triangles have other disadvantages. If you look at this has very high node complexity, because typically 6 triangles will meet in a node, and the manufacturing of these nodes can be very difficult. So you see here such a detail from a node where these steel beams meet together, and in the middle you see such a spider-like structure which is somehow the kernel of this node, where these beams are welded to this node. So this is another topic, substructure geometry, which is not easy at all. Then what does it mean to take an ideal panel shape? It depends, of course, on the material and the fabrication technology. And Frank Gehry, very well known here because there's also a Gehry building on this campus, he prefers, in his designs, he preferred sheet metal cladding. And a sheet metal behaves a little bit like a paper. So if you take a piece of paper, you can bend it into shapes, but these are special shapes. Yeah? You will never be able to bend a sphere out of this paper. These are special shapes. We call them single curved shapes. We'll say a little bit more about them later on. And for sure, if you have such designs, the single curved, or also called developable shapes, they are preferred. And Frank Gehry realized this. He founded a company, Gehry Technologies, which actually, for sure, also employed some mathematicians, and they developed software that was specifically designed to deal with these developable surfaces, and was then integrated into a well-known and frequently used computer-aided design system called CATIA. And you see in Gehry's buildings, if you look at the evolution of his designs, how they become more and more perfect with the increase of sophistication in the software. Now, another idea to simplify this is to use repetitive elements, so make sure that you have a lot of identical panels, for example. The problem is that at first you'd start with some design, some fancy design, and using tools that do not respect actually the panels which we place later on this design. And so there is a future direction which we are working on now, and where I'll show you a little bit, namely we develop design tools where you embed core aspects of this fabrication directly into the shape design process. And this avoids the current process, which is called rationalization, where you first design and then you think about building it. So it actually was interesting for me when I entered this field, which was actually by pure accident. An architect came to my office and dropped me a paper which he had seen recently and asked me whether I could solve this problem in more generality. And this brought me into this field. But usually it's like this. This project gets designed, and there's a competition. These are usually prestigious projects, so there's a competition. And before the competition, one would not think too much about the realization. Of course, one has some feeling, but only later on, if the competition is won, then it comes to this process where you have to make it buildable, which is called rationalization. And for sure, it would be benefit when immediately the architects had tools that are adapted to the requirements in this application. Or you have to integrate aspects of statics into the shape modeling phase. I will also show you an example on that. And there are more ideas I'm not going to discuss now. So the goals for this mathematics in architecture is to essentially develop novel computational tools which link design, function, and fabrication into a single software system, and to provide new mathematics for this task. And also to explore the variety of feasible designs. This is an important aspect. So in mathematics, we like to go for optimal solutions. We like to solve an optimization problem. But this architecture is an area that is related to art. And the architect wants to explore the variety of feasible designs and not just get one single solution that is said to be the optimal in a certain sense. So this also needs to be done. And how do I know about requirements in the real world? I know a little bit about it because I founded, together with my brother, a spin-off company called Evolute a few years back in 2008. And we have been involved in quite some real projects, and there we see what is actually needed in the application. So let me give you an overview of the rest of this talk. I will start by explaining a little bit the mathematics behind freeform architecture from flat panels. Then we will move to curved elements. Then I will show you architectural geometry in practice at hand of a recent project, namely the Eiffel Tower pavilions. Then we will talk a little bit about shape modeling with constraints from statics and manufacturing, and towards the end about repetitive elements, non-conventional forms of smoothness, and we will draw some conclusion. So let me start with freeform architecture from flat panels. Initially, when we think about such structures, we neglect certain details like the thickness of a panel or the beams which carry the panel, seams and further layers. So it can be quite complicated. This is just a small mock-up, but you see that it can be quite complicated. We just consider these flat panels, in this case quadrilaterals, pieced together, forming what we call a mesh. This is pieced together by flat quadrilaterals. And we call it also a polyhedral mesh, and polyhedral means flat faces. It needs not be quartz, could be quartz and triangles, or here also quartz and triangles. It could be hexagons or whatever. Pioneers in this field have been the German engineers Schleich and Schober, and they built structures like this. This is the Hippo House in the Berlin Zoo. And there the panels are actually trapezoids. And with these trapezoids, you can model some shapes. However, you cannot model general freeform shapes. So the question was, if we take general quadrilateral panels, can we model freeform shapes? Any shape, basically. Can we approximate it by these structures made from flat panels? And there, mathematics comes into play in form of differential geometry. I see a lot of high school students here also, and you may not have heard about this field, but you have heard about calculus in school. And differential geometry uses calculus to study geometry, in particular to study curved objects like this one. So a typical question is, assess the curvature of an object or of a surface. This is a pretty flat one, so the curvature will be low. Here the curvature gets higher. But if I look at this from this direction, it looks highly curved, but from this direction it looks a little bit curved only, or basically not curved. So studying this curvature behavior is one of the tasks of differential geometry, and it turns out that the layout of flat panels on a given surface is very closely related to the curvature behavior. And the relation is the following. I do not show you any equation, of course, but if we think now, this is a surface and we already have laid on it this planar quartz, and we pick a point, then it turns out that the direction formed by this one mesh polyline at this point, we can call it a tangent or so, and the other one cannot be independently chosen. You cannot choose both edge directions of this quads independently. As soon as you choose one, the black one, the blue one is determined. Or you choose the blue one, the black one is determined. This is called the conjugacy relation in differential geometry. And this is a limitation. And it can turn out that these directions are actually falling together. So they are totally unsuitable for this task. And this is a difficult thing which is not so easy to convey to somebody who just looks at this and says, oh, what, is it complicated to have these flat panels? Yes, it is. And it is related to a recent developments in geometry, which is called discrete differential geometry. So before I've said differential geometry uses calculus to study something. And in calculus, you take derivatives. And of course, the functions which you compute the derivatives from must have derivatives. It must be differentiable. You must be able to compute that derivative. But for a structure made up from flat faces, this is not really true. If you would apply the classical theory to a structure from flat faces, in the flat faces the curvature is of course 0, and everywhere else along the edges and in the vertices it is not defined. But there is now this trend of studying these discrete structures, as we say, these meshes and so on, where we extend the classical theory that it also holds for these structures. And these planar quad meshes formed from planar quads, are actually a discrete counterpart to what the mathematicians, the differential geometers would call a conjugate parametrization. Now, the final computation is performed with numerical algorithms, so a step-by-step improvement of the solution. You start out with something where the quads are nearly flat, and then you make them more and more flat iteratively. So there's an optimization procedure. And a success of such a procedure always depends, or often depends, on the choice of the initial guess of your solution. And this initial guess, in this case, is really done with help of differential geometry. I don't go into the detail, but without this differential geometric knowledge, it is more or less impossible to do it. So does this work in practice? That's the theory. Does it work in practice? We have to look at some real examples. This is already a real example. Unfortunately, it did not yet get built. I do not know whether it will get built, where the design surface is something developed by a CAD system, and here is the solution with planar quads. Here a rendering. It appears like a smooth surface. Of course, it is not totally smooth, which you see here in these reflection patterns that have these breakpoints. Another example, which was recently finished, this is in the Louvre in Paris. It is a museum of Islamic arts in one of the courtyards of this Louvre museum. Architects are Mario Bellini. Construction company is an Austrian one, Wagner Biro, and the geometry consulting was done by the spin-off company Evolut. So Evolut got this mesh from the architects. This is a triangle mesh. This is the roof of this structure. And the intention of the architect was it is a flying carpet. Yeah, it's Islamic art. And the problem with this triangle mesh is that it results in a heavy structure. There's a lot of steel involved. So the Wagner Biro, the steel company, said, can you make a solution from quads? Try to remove as many edges as possible and come up with a planar quad solution. And this was a huge failure. This is the result. It may look nice, but it is not well aligned with the boundaries. So the architect did not like it. You could come up with many other solutions. They did not like it. However, there was a solution which was a nice compromise, namely, you do a mesh which is formed by planar quads here and triangles. And then it was possible to solve this problem because you don't have to care about the planarity of the triangles, and so you get more freedom basically to planarize these quadrilaterals. And this structure was then built. So this photo is taken during the construction, actually from the room where the famous Mona Lisa from Leonardo da Vinci is on display. And you see here nicely these quadrilateral panels and the triangular panels. This is very well seen. And this is the final structure where you do not see it so well anymore, but it is now open and You can visit it if you go to Paris. Now, another task here would be, actually, we don't like general quadrilaterals. They can be very long and thin. They can be badly shaped. Glass typically comes in rectangular panels, so it's a question, can we build such structures so that these panels are as close to rectangles as possible? The answer is yes, but we have more limitations. Before, we could choose one edge direction and the other one is determined. Now, basically, the directions are determined. I'm not going into detail. Again, this is differential geometry. But the nice thing is we can express what it means being close to a rectangle in a more precise form. So obviously it is not possible to assemble rectangles so that in a tight way so that you approximate arbitrary shapes. This is easy to see. But what can you use? And there is one elegant solution which is called a circular mesh. This is a structure where all these panels are quadrilaterals which have a circumcircle. And maybe you remember from school, if you have a quad which is inscribed in a circle, then the sum of opposite edge angles equals 180 degrees. So you could say the average of opposite edge angles really is 90 degrees. So it is not every angle is really 90 degrees, but the average of opposite angles really is 90 degrees. There is another alternative which is actually better for architecture and which was invented because of this architectural application. It's called a Conically Mesh. A Conically Mesh is also a mesh formed by planar quadrilaterals, but now we have a condition at the vertices of this mesh, so here at these corner points. And we require that the planes which meet there, so in this case 4 planes, these quads lie in planes. These planes are tangent to a right circular cone. This is the cones you know from high school, which are base circle and the axis and the vertex on the rotational axis of the base circle. So being tangent to such a cone is a special condition, and again, you can express it in terms of angles. It turns out that if you look at these angles at the vertex, the sum of opposite angles, here omega 1 plus omega 3, is the same as the sum of the other opposite angles. I cannot say it is exactly 180 degrees, but the average is at least close to 90 degrees. And these cones have an advantage because it turns out if you take these cones, they have a rotational axis, they are cones of revolution, they're rotational cones. Then it turns out that the cones associated with the vertices of an edge have axes that line a plane. This is very easy to see. By symmetry of the cone, this plane is easy to find. But then you can place the beams, the supporting beams, in these planes, and then you get beams that nicely meet at this node, and this is called a node axis. So then with these beams meet in a simpler form than we have seen before in case of this triangle mesh. And this is a architectural rendering. This is not a real design, but these node axes in a real project appear here in this Yas Island Hotel in Abu Dhabi. It was another project of our spin-off company, and you can see the node axis here very clearly in this mock-up. You have here these beams, you have here this node axis, and on this axis the actual glass elements later on are placed. So here you have a view from the construction site. Now let's move a little bit toward curve elements and to what Frank Gehry is doing. He uses this sheet metal without stretching it or without metal forming, just by bending it prefers developable shapes. So once again, a shape is called developable. So like this shape is developable because I can unfold it into the plane by pure bending, without any distortion. So without stretching or tearing, I can bring it from a curved shape to a flat shape. That's developable. And these developable surfaces come actually only in 3 basic types that are super easy to understand. One type is a cylinder, which you know from school. The base curve is not necessarily a circle, an arbitrary curve, and it is formed by straight lines which are parallel to each other and meet this base curve. That's a cylinder for geometry. Or a cone. A cone is something which is formed by a family of straight lines, all of which pass through a point, which is the vertex, and meet some base curve. Once again, I repeat, I stress that this needs to not be a circle. It can be, but need not be. And the most complicated one is this. You take a curve and you take the tangents of this curve, and they also form a surface, and this surface is also developable. And these are the only surfaces, these and their combinations are the only surfaces which can be unfolded into the plane without stretching or tearing, and these are the ones which are preferred for architecture when you use sheet metal cladding. Now, there is a very simple relation to what I have said before, and I really want to demonstrate it because it is so simple. We take a strip of planar quadrilaterals, just a strip of planar quads, nothing else. And we think of refining it. So we're making these quads, more these quads, but approximating the same shape, and we keep doing so, but we make sure that these quads remain planar. So in the limit, I claim this must be a developable surface. And it's obvious because all the intermediate stages were developable because they are made from flat elements, from flat quads. And so we can now start with a mesh from planar quadrilaterals. We refine in one direction. We keep doing so. And at the end, we will get something that is composed of developable surface strips. We call it a developable strip model. And this is an interesting representation for a mathematician because it's somewhat smooth in one direction and discrete, as we say, polylines in the other direction. And it actually motivated some new research in mathematics. And one reason why I show it, because it is also used in the announcement of this talk. This is such a design with a developable strip model. But now let's go on into a real project. And this is in Paris on the Eiffel Tower. There was last year going on a refurbishment of the first platform of the Eiffel Tower. This is here, where they placed 3 pavilions, and these pavilions have a curved glass facade. And the question was how to manufacture actually this facade. And this was one of the rare projects where the mathematicians have been involved already prior to the competition. So for, of course, zero salary, you work for the competition, and later on, if you win, you get something. And the input from the architect was the design surface. This is this surface and a very rough pattern, which later got refined by some differential geometry. I don't go into that detail. And one wanted to place panels into these individual cells here, and one wants to make sure that these panels meet as well as possible, so the gaps are really small. Small gaps are okay because they can be hidden in this construction, but this divergence, as you call it, should be small. And these kink angles, these deviations from smoothness, should also be at least controlled, but preferably small. One solution here is actually to use planar quadrilaterals, and it worked because these seams were already following the rules of differential geometry which are necessary to make planar panels. So this is one option, but the architect did not like it because it looks too faceted. For sure you want a smooth facade, and this looks too faceted. Then the idea was to use these developable strips. This looks pretty good, but it has a severe disadvantage because a general developable surface cannot easily be built from glass. So to bring glass into a general developable shape, you still need a mold, and this is too expensive. So there is curved glass around, like here in the train station in Strasbourg, but there one prefers shapes of these panels, glass panels, which are right circular cylinders. The cylinders you know from high school. And there are special machines which bring the glass into this shape. So the question is, can we do it with right circular cylinders? Well, this is obviously a mathematical problem. Let's concentrate on one of these strips here. So we take this upper element here, and we compute the cylinder which best approximates this element in this face. I draw here the entire cylinder, but of course only this small part of the cylinder will be used. And then you do the same for the next phase, the same for the next phase, and then something interesting happens. So far, most of these rulings, of these straight lines on the cylinder were more or less vertical, but now it totally switches to more horizontal, then the best fitting cylinder looks like this, and we continue. And then we can look at the quality, and the quality is at first judged by these gaps. Here, 26 millimeters is not tolerable, it's too big. So one has to do something else. Well, of course, so far the solution was too straightforward, because you just pick an element and you compute the best fitting cylinder, and then you pick the next element and so on. One can do it at once. One can globally fit the best cylinder everywhere and make sure that these errors get smaller and smaller. And this was done, and this brought down the divergence quite a bit. The kink angles would also be fine, but the architect did not like it. If you look at this rendering, you see immediately why. Because you see this transition. In this upper part, these straight lines on the cylinder are roughly here. In the lower parts, they are more horizontal, and this transition doesn't look nice at all. It catches immediately the eye. So this was actually preferred. Avoid that this cylinder flips this direction. Then still, it was not perfect, because there were seams along which this kink was pretty sharp, maybe something like 10 degrees, and there were other seams, like here, you see it even in the shading, where the kink was small, maybe 1 degree or so. So it was the goal to more equidistribute these kinks, and this was, of course, possible, and that's the final solution. The divergence of these gaps are less than 3.6 millimeter, which is really good. The kink angles along strips are extremely small, and between these strips, they are controlled and everywhere nearly the same, and this was realized. And you see here an image from the construction site. Unfortunately, I do not yet have an image from the final design, from the final object. I doubt that it is already open to the public, because otherwise I would find some images on the web. By the way, the subconstruction here is interesting as well, and without going into any details here, I mentioned that even for this subconstruction, these developable surfaces are important, and to some extent, this example is a little bit like a lecture in differential geometry. So for the experts, they know that along a principal curvature line, the surface normals form a developable surface, and this is used here. Now we look at shape modeling with constraints from statics and manufacturing. And we look at this. So this is something which is self-supporting masonry, just standing, theoretically even without mortar, just by the self-weight of these elements. That's a generalization of what you know from these classical arcs that are used in architecture. This is research done at ETH Zurich by Philippe Bloch. He was interested whether it is possible to build such masonry in freeform shape, and this is a demonstration. We have been interested in more the mathematics behind, and also in tools which allows one to create such shapes. Relations to geometry, and also to make sure that the structures which we also like this planar quartz panelings with the substructure, is also in static equilibrium. So we assess the statics as well. Yeah, this I'm not so sure whether I should go into any detail, but I mentioned that this is based, of course, on some mathematics to check whether this is in static equilibrium. And one way of doing it is a so-called thrust network analysis. A thrust network is a network of compressive forces which is inside the envelope of the structure and which balances the load. So these are here the edges of this network. We have here the forces, and actually these forces counterbalance the self-weight of the structure. They hold it. And if you can find such a thrust network, this will stand. It will be self-supporting. And if we have materialized only the beams, these forces have to be along the beams, of course, and if The material is steel, and we have some welded nodes. Of course, also tensile forces are allowed, not only compressive forces. And the result we could achieve is this one. This is a terrible design. It looks really ugly, but it is surprising because it is self-supporting while having so many holes in it. So it's not easy to, if you show it to an architect, they will appreciate these many holes. This is not so easy to achieve. This I will skip. And then I will talk about something which we really aim at. So what I have shown you before, some of these projects have been a kind of fire brigade. At first you design something, and then at some point there's trouble, and then we help out and try to resolve it. But ideally one should develop tools that allow the architect to consider important aspects of the actual production, like flatness of a panel, developability of a panel, the statics. You should consider it already when you do the shape design. And now I may shock some of you, the mathematical expression of the above. The above is given a mesh, I make it simpler, so mesh, modified so that it fulfills the constraints from statics and manufacturing and is suitable for the specific application, for example, is aesthetically pleasing. The mathematical formulation would be, given a point outside a constraint manifold, but reasonably close to it, project this point onto this manifold. So how do I come to this strange formulation? In this problem above, we have some variables involved, like the coordinates of the vertices of this mesh. There's many coordinates, many design variables. And if you consider all these design variables, you can consider them as coordinates of a point in a high-dimensional space. And then you have some constraints which you can formulate in terms of equations and inequalities. And this will limit the locations where this image point in this high-dimensional space can be, and it breaks it down to what we call here constraint manifold. And one has to project onto it. Now, even more surprising, it is interesting that we have to be more efficient. It helps to add even more variables and to make sure that the constraints get simpler. Simpler, I mean, we introduce auxiliary variables so that the constraints are at most quadratic. What the quadratic equation is, I'm sure you know. So at most quadratic. I give you a simple example involving just very simple analytical geometry. In order to check whether a polyline with vertices V1, V2 up to, say, V10 or so, VR in general here, is planar, we introduce as an additional variable a normal of this plane and express the planarity just by stating that the edges of this polyline must be orthogonal to the normal, which is this vanishing of a scalar product. This is bilinear, a quadratic equation. We will do this for all n edges, also it is not necessary. If we have an n-gon, n-1, conditions would be sufficient. So we actually introduce constraints which are dependent, but in the constraint solver we use, it is not a problem because we use the most simple form you can imagine. This involves a little bit more mathematics than you may know. Some of you may know we linearize the constraints. This gives a badly behaved underdetermined linear system, but then we use a regularizer. We use, say, something that judges the fairness of the object or make sure that it doesn't change too much, so judges the proximity to the original. And this set up the conditions for an unconstrained minimizer of this additional objective function, which will make sure that it is a quadratic function also. And then we get more linear equations, and we end up with actually too many, and we solve them in a kind of compromise, which is known as a weighted least square solution. And we iterate this. And it turns out that this is sufficient to come up with software that reacts in real time, and I would like to show you a video on that. So instead of more mathematics, let's just look at the video. So one moment, I failed to integrate this video directly into the presentation. Here it is. So this is how we would like to see these modeling tools, just simple examples. We start from a flat mesh, and the user just drags these vertices, and the structure always follows by keeping planarity of faces. Planarity is indicated here by the blue color. Whenever you see something red is bad, but it turns blue quickly. So this I would call interactive modeling. Or with more faces, it takes a little bit longer then, but still the user can really manipulate this structure and always make sure that these constraints on, in this case, planarity of faces is maintained, and then this is the final design. You start with a non-flat boundary, works as well. A lot of red around, so very non-planar, but quickly it adapts to planarity. And you see, we keep the boundary, but the vertices are allowed to glide on this boundary. That's very important. So this is really interactive. Or it needs not be planar quadrilaterals. I may have overemphasized that here so far. So this is something which is composed of hexagons and triangles. You see these hexagons popping up, but quickly they become blue, which means the planarity is within tolerance. So the interactive modeling of such a structure, which has, I think, about 3,000 vertices or so, is possible now. And if you do it like this, you have do not have the problem that later on you have to worry whether you will be able to make it, in this case, from a pattern of planar hexagons and triangles, because you have already designed it in this way. Yeah, you may not be able to see it in the back that this is composed of hexagons, planar hexagons and triangles. Now we add statics, and we look at static equilibrium, and also keeps the planarity of the faces. And you see here the user manipulates this structure. The colors shown are the forces, the stresses. Blue means tensile, and red means under compression. So currently we have more compression. But then the user wants the structure to lean forward, and of course this introduce tension forces in this direction, and you see immediately that it turns blue here. However, it is of course possible to require as an additional constraint that these forces are all compressive, which means we get a self-supporting structure. And again, a structure with an overhanging part. And now let's make this experiment. The user tries to check whether this object can really lean forward, but it resists. It has to resist, because otherwise you would need tensile forces, and they are prohibited here. Yeah, and this is the final result and some rendering of it. So let me come back to the presentation, and we are almost done. At last, we would like to get some inspiration from nature. If you look at this is a honeycomb. It's not the one which you are used to, the flat one, but the bees are also able to produce structures like this. And we were interested whether we can make use of that, because the bees like to build 120-degree angles. And the question was, can we come up with such hexagonal structures so that adjacent cell planes here really meet at 120 degrees everywhere. So all angles here are just 120 degrees. That would simplify, of course, the construction. Is it possible to do it freeform? And it turns out it is. You can even manipulate not only the shape of the structure, also the directions of these axes at the nodes. Here you see an example of a shading structure which has been designed so that for given sun positions it provides shade. From the other side we see that this is really such a hexagonal structure. You can derive things like this so-called reciprocal structure where you resolve the nodes, and such things have been realized also. There's lots of geometry involved. And finally, we come to a solution for this Louvre Museum of Islamic Art. It turns out that for this geometry which I had shown you before, this flying carpet, you can build a support structure which has this hexagonal pattern, this honeycomb structure. These hexagons are not flat, they are not planar. But you can cover each hexagonal cell by 2 planar quadrilaterals. In this form, you get a pattern of planar quadrilaterals, which is different from the pattern we had before. Before, we were aiming at something like this, so these smooth polylines. Now we have something like this. In one direction here, it's smooth, and in the other, we have this zigzag. But it is controlled. It is a pattern, and it also has some aesthetics. And obviously, we have here more degrees of freedom, and it is totally unclear how much one can say as a geometer, as a mathematician about these structures. This is very recent works, maybe just a few weeks old or even less. And this is only a few days old. Another pattern which looks nice, and actually it would be a nice pattern for a museum of Islamic arts. It is also just from flat quadrilateral panels, and it involves some interesting geometry, I think. With this, I would like to stop my elaborations, and I would like to conclude, and I hope I could show you that there is some mathematics involved in this freeform architecture, and the mathematics really helps to build such structures. I have hopefully shown a little bit that the mathematical disciplines which are involved are mainly differential geometry and some numerical schemes like constraint solving and optimization. The mathematics forms, and this is the beauty of mathematics, even if we develop these tools for architecture, they are useful for other purposes. So it's not just for architecture. This is about novel computational design tools which combine shape modeling with aspects of function and fabrication. We believe it is applicable to many areas beyond architecture, and we have some initial studies on that. And finally, I ask myself the question as somebody who has taught geometry for architects for many years. So since 1992, I have taught geometry classes for architects, and I always have some difficulties in explaining certain things because, at least in Vienna, mathematics is totally out of the architecture curriculum. So my question is, wouldn't it make sense at least to offer some mathematics for the interested students of architecture and design? Because I think it is reaching another level of creativity if a designer can, to some extent, build his own tools. The tools somehow influence what you actually will design. So this freeform stuff comes because the tools allow you to design it. And so I believe that being able to design your own tools is a very innovative thing. Involves a lot of creativity. And so I would advocate for increasing the role of mathematics in the curricula of architecture and design. And with this, I would like to stop and thank you for your patience with my talk. Thank you.
Well, thank you very much for a fantastic talk. I think we will answer a couple of questions from the audience. Please raise your hand if you have a question. No? Give you the microphone.
Thank you very much for a fantastic talk. My question is how, for example, the safety of the architecture or structure, such as earthquake, resistance of.
Thank you for this question. Thanks a lot. Because
so how come?
Yeah. So I forgot to mention that when I had this simplified model of assessing the statics, this is not meant of removing the engineer. This is just to make sure that the engineer has less trouble. We, of course, also checked these structures later using ANSYS or some of these usual tools from engineers, and they do stand. And, of course, they resist additional forces. It would be terrible if there is some snow and it breaks down, or there is strong wind and it breaks down. Yeah, sure. Thank you for this question.
Anyone else?
Oh, yeah, sure. This is the next thing we want to look at. So we want to look at patterns, other patterns, which can be used here. I think it is a wide open field. There is a lot to do. Yeah.
Anyone else?
Okay, how about the use of quasi-crystals in something like a museum of Islamic art?
Lots of possibilities.
So for the architecture students, you know where to sign up for math classes. Come visit our webpage. So I want to thank Professor Helmut. Oh, there's one more question up there.
I can just. You said that it used to be that the architect firms would bid for their designs first, and then they win, and then they do the realization. Has there ever
That's usually done, yeah.
Has there been any design that's unrealizable?
Unrealizable?
Yes.
Of course. I showed you some. So this, I didn't mention it. This one crazy shape which looks like a gold nugget, it was a design for a bank in Abu Dhabi. It did not get realized because it was invisible. Yeah.
Okay, so I think we'll end here. Thank you again for a wonderful